So now we are leaving the skeletons and going to touching items instead. So what you saw last week was that these touching items, they were labeled as the same. So now we want to know a little bit more about it, how to improve. And one thing is that we're coming to an algorithm that's called Watershed segmentation, and it's used very much in very many applications, also as post-processing, even for machine learning tasks. So here you see an example where they did some segmentation, identified a structure, but in the end, they want to know where each one of these objects are. And for that, they did apparently a bunch of morphological post-processing and watershed segmentation. So watershed segmentation is the keyword here. And let's look at a cell image. The original looks something like this. Then we convert it into grayscale. There is some segmentation of it. This was just a thresholding, but as you can see there, for example, here, some very faint objects. And then for the training purpose, we even have a labeled, let's see. Yeah, there it comes. We have a labeled ground truth. So that is labeled by someone who knows the objects we are looking at. And first, my pointer is misbehaving. Yeah, there it is. So on first view, you can already say that this doesn't much look like this. So there is something more to be done. And the first thing we start doing is to try component labeling. And when you segment it, you can see that we have these dark regions that would be the cells. And then there is some bright in between. So that would be the substrate in between them. And component labeling would give you one object here and one object here, as you can see here now. But the ground truth tells us that we should have actually 4 objects in the same image. So this wasn't very good segmentation or labeling. So instead, we are using the so-called watershed, and the principle comes from the analogy of water running downhill in the landscape. And you can have, this is actually a view of the two, of the cell that we looked at just before. And let him. Okay, so what we do is we create an elevation map based on the black and white segmented image. And then we, in this case, I have visualized it as really as a landscape with nice colors, snowy mountains and water in the bottom. But the principle of the watershed segmentation is, if you would let it rain here, the water would run either down in one valley or the other valley. And if it rains a lot, the water is rising. And at some point, the water is rising to this level here. And then the water touches. And water starts to touch, then you start building a dam. And the water is rising even more. And you build up the dam. And in the end, you will have a landscape with only dam walls. And those are segmented regions. So that is the principle behind the watershed segmentation. And let's look at the same case that we had before. And we have the segmentation, we compute the distance map, and we can see that we have one maximum here, one maximum here, and one here. And here is actually a saddle point between them. And this find the peak local max actually finds the saddle point too as a maximum. And these would be the seed points, the points where we start filling in the water. And then the water is rising and filling up the regions. And after the watershed segmentation is running, we get this image, which starts looking actually quite a lot like the one we had before. So this is a good start. What we do have is one region here in between, which corresponded to the saddle point. And we actually missed the one up here, but that is probably more due to the thresholding that we used instead. So it's not, doesn't have anything to do with the watershed itself. So that would be going back one step in the process. Then we can start removing two small elements. I mean, if you have structures the way you know that they should be distributed within some bounds of size, then you can say everything that is smaller than that we reject and throw away. And in this case, we have the bottom 10 percentile of areas, and we can see that looking at the area, we can see that the area of label 1 is 82, that we keep. We have area of label 2 is 7, so that's below the threshold, so throw it away. And the remaining 2, they are also above this threshold, so let's keep them too. And the pruned skeleton from that is, no, that wasn't meant to be, is that we now, instead, we have removed the local maximum here for the saddle point, but the other 3, they are still remaining. And we get something looking like this. And the ground truth was more like this. There is still a difference, but this difference, I would say, is more about how the thresholding was done and not about the water shedding. So now we have identified our 3 items that we can identify. And that would be good. So let's running it on the whole image with all the cells. And that requires some coding. Again, we have here, we do, just to explain what's happening. First, we do thresholding and some opening to clean up. Then we do the distance transform to get the elevation map. Locating the local maxima based on this distance map, and cleaning up a little bit and label the peaks. And finally, we run the watershed on this image to get a first segmentation. Then we realize, okay, we have some over segmentations, so we also run the 10% small objects and clean them off. And apparently here, 25 of these components were removed. That looks like this. And as you can see, there are some over segmentations, and the ground truth isn't really looking as it should. No, it doesn't look like the ground truth. And what we have is, in particular, one thing is that we have a lot of over segmentation here. We have a lot of missed items around here. You see that we even don't even segment this part right. So the first thing is we should actually look for a better segmentation algorithm to identify the cells in the first place. But then we also have the problem of these over segmentations, that we have a lot of places where the items are cut up in very many small pieces, sometimes very extreme. This one, which is more or less pixel after pixel, is labeled up into small regions. So why do we get this bad performance? The reason is we have in the landscape, the objects are not perfect round objects. And as soon as we have some kind of peanut-shaped objects, then we have distance maps that create actually two regions. Even though it's one, the place where the peanut is getting narrow is producing this effect. Another reason is that we have misclassified pixels, and that would also produce this kind of effects. So here I have two misclassified pixels, and instead of having a distance map looking like this, which would produce a single object, we get that instead, and here you would get a watershed segmentation that splits this disk into two. So the first thing is to find better ways to segment the images. And there we already looked at several ways. And the other thing is having a different way of identifying where you have the local minima and maxima. And there are a couple of methods described in this book, which I can highly recommend if you want to look at morphological processing. There are two algorithms. One is called hmax, and the other one is min-impose. These are based on algorithms called reconstruction by dilation and reconstruction by erosion. And it's kind of an iterative local minima or local maxima algorithm, where you start out based on a mask. And what the hmax function is doing is you say, what is the maximum peak or the peak height that you at least have to achieve? That gives you a point. So if you have small local maxima and they are lower than this threshold, then they will not be considered as local maxima. And the other one is min-impose. That's kind of, if you think about having a membrane and you pull it, then you get like a very funnel-like effect. And that is what this min-impose is doing. So just to compare what these algorithms are doing, if you look at the peak local max, you found this saddle point. hmax wouldn't even find the saddle point to begin with. But anyway, here I set hmax with a height of 2. So I need at least a peak of 2 gray levels to consider it being a maximum. And then I got the 3 regions, which I was looking for. And the other one is min-impose. And yeah, it maybe look a bit strange here, but in principle, what we're doing is we are taking this map with the peak points in it, and say that on these points, I want to go really deep. And the Tmax is some value that you set. Sometimes people talk about infinity. It's a bit extreme, but at least something that is the beyond the maximum value of the image or the elevation map, or a little bit more even. And then you can run it like this. And what we do when we look at what's happening is first we need to get the distance map. And when we run Watershed with the first method that we did before, it looks like this. And if you run min-impose, the difference you can see is that here, the minimum, and here the minimum, this one is much more localized. And the same up here. This is a wider area, and this is more localized around the point of the seed point. And a bit disappointing, actually. In this example, it doesn't look very much different. So let's look instead on the effect on the segmentations. And now you can start seeing that we have actually less wrong segmentation, and it's not so easy to see. So here is one example down here. You have some examples down here where you can see that this one was nicely separated and you have two big grains. This one is now classified as a single, as it wasn't here. So it actually performs better, but the problem now is actually the color map. Because when we look at this, these regions, they are labeled 1, 2, 3, 4, 5, and so on up to the maximum. And if you use a continuous color map, like, for example, the Viridis in Matplotlib, then you would get something like this. It doesn't tell us anything about the labels, and it's very hard to distinguish if this one is a different label than that one. We can't tell it. So instead, there are a couple of discrete color maps. So there is the tab 10, tab 20. But the problem with tab 10 is that the items are divided into 10 groups. Tab 20, then the items are divided into 20 groups. But in this case, we have much more items, and that's why we don't see what we actually are looking at. So instead, what I cooked up was to use two different color map cases using either completely randomized colors. I did some orthogonalization too to make them sure that they're really separated. Or else using the golden ratio on the HSV color code. So that would be the hue. So that's actually a value that goes from 0 to 2 pi. And then I use the golden ratio to find different colors which are irrationally distributed and also not very correlated between them. And looking at this, then you can all of a sudden compare and see that with tab 20, we have very hard to distinguish which ones are separated. And then using the random and the golden ratio, you clearly see where you do the misclassifications and also where you have good objects. So these two are recommended to use actually, or something like it are recommended to use when you are looking at watershed segmented, or actually labeled images with more labels than the color map can handle. So this actually creates one color for each item individually. So now I have a use case about separating grain packings. This was an experiment I did a long time ago. We had two sand fractions and we wanted to look at the interface between them. So we filled in relatively fine sand grains. No, I think we had a coarse in the bottom. Coarse sand grains, and then on top of it, we poured finer sand grains. And then we wanted to see how what happens in the interface with the porosity between the two grain packings. This is a 3D analysis. So we have 500 by 500 by 300 voxels. And now the task is to separate these two fractions. And the first thing is setting up a workflow, a nice recipe. First, of course, load the data. Then we need to do noise reduction, binarize the images, clean out some misclassified voxels. So that's more or less actually going through the different lectures we had already. Then the next step is labeling the grains. And then we do use the watershed segmentation. So first we need to compute a distance map, identify and label the grain peaks, and then run the watershed segmentation. After that, we want to get some statistics out of these images or these objects. So we want to compute the region information. do some filtering, removing tiny and huge objects, and then looking at the region properties, and finally do some k-means clustering. And the very last task is to actually assign pixel values or fraction class labels to the upper and lower part of the data. So that would be the outline for what we want to do. In this case, I'm jumping in the middle of it, so I don't do all the filtering and binarization, etc. So we have already a bi-level image, and I even cheat having the water segmented data just to save some time. The focus now is actually to do the analysis based on the grains that we got. And then we can run the region props, which you already have seen, to extract the label, area, and centroid of each grain. We get from that a long table with all these informations. You can see the label numbers here. We have quite many items. And from here, you can see first we have the minimum area is 1 pixel. And the maximum area is very large. But it doesn't match actually with the median area, which is around 12,000. So that means we have on one side regions which are misclassified based on misclassified pixels. And we have a very large one, and the very large one, that's background. So that's the whole pore space. So let's do some filtering on this table. So I'm actually not looking at the image anymore. I'm looking at this data table with this information. And we see, okay, if the area is less than 10 to the 7, then we keep it as grains. And the other thing is to check if the area, or actually volume, is less than 1,000, then it's considered to be a small item. And what we get then are 2 extra columns. We have here, is it foreground, or is it small? And from those, we can separate out. We have our grains are the ones that are true here and false here. And that is the information we're going to continue working on. And if we look at the pruned results now, then we can see that we have a volume histogram looking like this. And we have also a centroid distribution. And you can see that it's much more compact packed here, and it's more sparsely here. So we can already see from the positions that we have 2 different sizes if we assume that the grains are touching. So that is a good information to begin with, but now we want to know actually where is this interface between the 2 grains. And looking back, on this slide, you can see that we actually have the interface would be somewhere around here, but there is some overrunners here that peak up. And now we want to find where is this interface. And the first thing I look at is the pair plot to look at all these parameters that we have, the histograms pairwise. You have the labels, they're just a flat line. Then the next one is the area versus label. Then we have the centroid in 0. And we have the centroid in 1. And we have a centroid in 2. From these, we can say already that those 2 don't make much sense. But this one, then you can already see that there is a separation between the area and the label. And at the same time, you can also see that there is some connection between the label and centroid 2. That would be the Z component. On these, we could actually use them. So that would be connecting centroid 0 versus centroid 2. Could make sense. You can also see again that one part is denser and the other part is sparser. But it's not so easy to really identify anything from it if you compare to the other two. So what I'm focusing on now are just the label and area and centroid 2. It's actually strange that the label is connected here. In principle, it could be anything, but purely algorithmically, the label is actually connected with the position because it starts from the 0 corner and runs sequentially through the whole image, going down and down and down. And when it first approaches the large objects, of course, there is a strong correlation between label and position. And then further on, you have the small objects and you have the same thing. So that can actually be used to segment in this case, but if you would have randomized objects, then it wouldn't be that obvious. Then you would have to look at something else. So this looks like a nice case for doing some kind of clustering. And the question is how to do this. Maybe someone you could propose something, how to find a way to separate the two clusters. One way would be actually to draw a line across just here, saying everything at this knee would be below this knee would be grain type 1, and the other one would be grain type 2. We can also look at the 3-dimensional case where we have label, area, and centroid, and then maybe it's not so clear to look at from this view, but you would have the same thing, but you have a spread also in this direction. So what I'm using here now is the k-means segmentation, and I run it, and the first run is actually disappointing because I don't get the cut here at the knee as I expected. I actually get it somewhere out here. So I have actually the different object sizes in the same class, which I don't like. And also, if I look at the grain positions using this segmentation, you can see that there's just a random mix, more or less. So the reason is for this is that the grain area is much, much greater than both the label and the centroid. So what we need to do is to scale the area in a way that it comes in the same size as the other ones. And that is something we did already when we looked at the k-means for the cortex segmentation. If you remember, we had that the coordinate, they made that we had the 4 quadrants, but nothing else. And then when we rescaled the positions, then we started getting some more realistic information. So this is the same thing again. And if we now scale by the area by some factor, I think it was, or actually I think I normalize it actually. So I'm normalizing, so it's minus the average of the grain size label divided by the standard deviation. So I do the same normalization on all. And when I do that, then I get a very nice cut line between the two sizes. And that now gives us a nice separation between class A and class B. And then once we have the two, then we can start doing more analysis on the two fractions. And we can see that the grain size varies. Actually, there is an overlap between them, quite a large overlap actually. And you can see that fraction A has much larger objects than fraction B. But there is some overrun here. And the last step would be to assign the classes back to the image and see how it actually looks like in the image. And then for that, I wrote this little function that more or less imposes, says that this centroid has this label, and then it's let it grow out in each object. And the result is something like this. And it's actually looks making quite good sense, I would say. There are some misclassifications around here. Maybe it's because of the size. I don't know right now. Actually, I didn't look at it in 3D. Another thing that is a problem when you do this kind of labeling is actually the boundary grains. As you can see, even though it's a lot, we have some large grains here, thanks to the cropping, they appear as very small ones. So there are also cleaning algorithms that check that all grains that touch the boundary of the image, they are removed or not included. So that is a way to handle that problem. Now I did it a little bit crudely, just by saying if it's too small, reject it. But the better way would actually be to remove the things touching the boundary. And then I look at the boundary interface. So this would be the distance from bottom, the average distance. So it's if you have grains looking like this, and then they probably have some connection here. So what I'm computing in this image is the medial position between the grain minimum and maximum from the two packings, and then I get this surface. Then it looks like this. And that was the end of today's lecture. So in summary, we have looked at skeletons, which displays the minimal structure that topologically preserve the shape of the object. It should have the same number of endpoints. It should have the same number of branchings. Is maybe difficult to say from a more well-grown object, but anyway, it should be branching in the same way. It's ideal for very thin structures to analyze how they behave. So it would be for streets, root structures, rivers, etc. And the other one part today was actually more a follow-up on last week's lecture, and that's the watershed segmentation, where you are able to label the touching grains. It's a very popular algorithm. It's used a lot, but the problem is that you have to pay attention to is that it may and most likely will over-segment the labels. So there you have to have strategies how to handle that, either by some smart maximum minimum effect filtering, and also by imposing different minima and maxima in the images. Yeah, that was it for today. Next week is about statistics to compare different groups. And I will also talk about, I think there's also data frames and how to plot and present results. Data frames is something that has been hidden in the lectures. I'm using it, but I'm not really telling what I'm doing. So for example, today in the grain analysis, I used this data frame, and that's like kind of like a database, but more about that next week.